Hello everyone. In this video we will talk about the infamous infinite series. Okay, so they are a bit infamous, but my goal is to convince you that you've already seen some of these concepts and that series really aren't that bad. So what is a series? So usually you'll see them written like k equals 1 to infinity of some ak term. It's very similar to a sequence. The main difference, of course, being that we have this big sigma guy here saying that instead of just listing our terms, we're adding them. So we have a1 plus a2 plus a3, and then we go on forever, and we end up with something just like improper integrals, right? Where, okay, maybe we have this infinite space and we think that this should be an infinite area. Sometimes it turns out to be finite. And so here, sometimes we will see that you can add up a bunch of numbers, not all zero, and still get something finite. So it shouldn't be too surprising after seeing improper integrals, but it still may feel a bit strange. So what are some good examples? So classic one, just an important one for improper integrals as well, was k equals 1 to infinity of 1 over k. So here, right, we would be adding 1. Next term would be 1/2 plus 1/3 plus 1/4, and so on. And this will be another one where, okay, eventually we're adding something really, really tiny. It's getting close to 0. The question is, does it go to 0 fast enough for the sum to be finite? We can compare it once again to 1 over k squared, right? Just like we have 1 over x versus 1 over x squared, the integral from 1 to infinity. And so here, right, we go to 0 a bit faster. So we have 1 plus 1/4 plus 1/9 plus 1/16, and so on. And so our terms get smaller faster, and so our sum maybe has more of a chance to be finite, we might think intuitively. For one more example, let's look at something like this. This is what we would call an alternating series. So alternating because our sign is changing every time, right? So if we plug in 0, we have -1 to an even power, so it's 1 over 1 or 1. And then the next one will be minus 1/2 plus 1/4 minus 1/8 plus 1/16, and so on, right? So you keep switching your sign every other time, or every time, and it's positive every other, negative on the other ones. And so again, our terms are going to 0, but yeah, we don't know whether this is going to actually give us a finite sum or not with our current abilities. We will actually come back to this one in a little bit. So as we often ask, we wonder why do we care? Why should we care, at least? So you may remember back in Calc 1, if you had some function, we could use a tangent line approximation to our function. And so basically you would turn some potentially weird function into something that if you zoomed in really close, you had a line. And why was this nice? Well, lines are really easy, right? You have something that looks like ax plus b. Well, I can definitely take the derivative of that. It's very quick. I can plug things into that. It's also very quick. So this is super nice. The problem was not very accurate, right? So as long as your function was curved much at all, if you zoomed out much at all, it wasn't going to be a very good approximation, right? It worked really well for lines, but not for much else. So what can we do? Well, it turns out you can just keep taking more derivatives, right? So the first derivative gives you the tangent line, kind of matches the slope. And then if you take the second derivative, you kind of match your concavity, right? And so you can match concavity with your function using the second derivative. And I won't go through this, but yeah, you can keep getting closer and closer approximations the more derivatives that you use. So these are things called Taylor series, which we'll get more into later. But basically, the point or the crux of the matter is the following. We can write well-known functions that may be hard to deal with in terms of basically make it an infinite polynomial. So this is e to the x, our nice friend, and it turns out the terms of this, so this is 6 or 3 factorial, 2 is 2 factorial, so this is secretly a factorial here. And basically what you get is you just keep raising the power by 1, and you divide by the next factorial. So in sigma notation, right, this would be the sum from k equals 0 to infinity of x to the k over k factorial. And it turns out this infinite sum is no longer even an approximation of e to the x, it's actually exactly equal to it. And so this is very interesting and also super useful, because if you want to plug something into e to the x, for instance, you want to get e squared. Well, if you don't have a calculator on you, I don't know what e squared is. On the other hand, I can definitely plug 2 into the right? I just 1 plus 2 plus 2, because 4 over 2 is 2. Then I get 8 over 6. And basically, you keep getting nice, easy numbers to plug into. You can do similar things with sine and cosine. They also have very nice series expansions that look somewhat similar to this guy. And so it's very nice to use polynomials to approximate things, because polynomials are super easy. And so this is kind of one of the main motivations for coming up with series and dealing with them, is to use easier to deal with things to approximate harder to deal with things. Okay, so we've talked about what a series is, why we might care, but like, how do we actually compute these things, right? With integrals, we could just do the antiderivative once we put it in terms of limits and just like compute these things, get a number out if it converged. So if I write the sum from k equals 1 to infinity of ak, basically what I'm going to do is turn it into a sequence. So again, we want to approximate by finite things. And so, for instance, we know quite well how to deal with the sum from a1 down to some finite n, right? We can add up finitely many things. That's easy. Well, that's what we call Sn. So this is the nth partial sum. So partial sum is the name of this thing in general. And another way to view this, right, if you want to use sigma notation, this would be the sum from 1 to n of ak. And so this gives me a sequence. So I can talk about the limit as n increases, right, as I continue to take more and more summands in my sum of my partial sums. So I'm adding more and more terms, and then this, call it s. If this s, this limit, is finite, then we say that our series converges. And we would actually say that it's equal to s. And otherwise, we would say that it diverges, just like improper integrals. Either converges or it diverges. So let's look at a couple examples here. So this one on the left, like, what are our partial sums? So S1 is 1, S2 is 1 plus 1, or 2, S3 is 3, and we keep getting this, right? So Sn is n. And it turns out, as you might expect, if you keep adding 1 over and over and over, well, you just get bigger and bigger and bigger. And, of course, the limit of n as n goes to infinity is infinity. So this guy would diverge. On the other hand, let's look at this guy. So here, we start with -1, right, because we have an odd power. And then S2, we have -1 plus 1, which is 0. S3, we're back to -1. S4, we're at 0. And this keeps happening, right? So Sn is going to be -1 if n is odd, and 0 if n is even. And so we just keep bouncing back and forth between -1 and 0. And so what can we say about our limit? Well, it just doesn't exist, right? It doesn't approach a single number. And so this diverges too. The key is, again, just like improper integrals, it's like a different kind of divergence, right? So the one on the left blows up and goes to infinity, whereas the one on the right just doesn't approach a single value. All right, so for your first exercise, I want you to look at this series of 1 over k minus 1 over k plus 1. This is what's called a telescoping series, as I hope you will find out why while looking at this problem. So I want you to write the partial sums, figure out a formula for this for general n, and then determine the limit if it exists. So maybe it converges, maybe it doesn't. Your goal is to find out. and it will help if you can find a nice formula for the nth partial sum in general. And for your second one, I want you to be able to write this in sigma notation. And specifically, I want you to actually start at 0 instead of 1 this time. So you should make careful note of two things, right? So one, you want to find a pattern between how you're getting from one term to the next. And of course, you should make careful note of the fact that you are changing signs every time. So this is going to be a special kind of series that we will analyze first. It's one of the nicest ones to see and one of the easiest ones to deal with, but it helps to put it in sigma notation to be able to recognize exactly what's going to happen. All right, thank you for listening.